Okay, take a look. ANN stands for artificial neural network. Let me show you. So here I give you. So this is what I want you to do. So this one will be you will include this in your paper, in your presentation. So here is so the first one, the performance comparison among the various ANNs that have two hidden layers in terms of error and the time taken. All right, so you need to compare the different ANNs performance. So you need to write these comparisons in a table. In addition, for this table, please do not use normalization. Normalization is one concept. So normalization means that for the input, the variable, we have this is a minimum value and a maximum value. If you do not normalize the input, and you will get the actual variable value. However, normalization means that you want to map this is a variable into an interval between -1 and 1. Okay, that means the minimum value of the physical variable corresponds to -1. The maximum value of the physical variable value corresponds to the positive one. So normalization means that we want to map these true values into an interval between -1 and 1. -1 and 1, this interval will give us a lot of advantages when we train the ANN in terms of the time it takes and also the accuracy of the results. So here, in addition, I need at least 2 performance curves, and from this group of ANNs performance group, I'm going to show you and how to get a performance group. So you see, please note that the first hidden layer contains varying number of neurons from 10 to 30. That means from 10, 15, 20, 25, and 30. So you will for the first hidden layer. A second hidden layer, and you keep using this is the 10th hidden layer. Okay, so I just want to, for this is different ANNs, the second layer is the same, and which means that they have 10 hidden neurons, but for the first layer, the number of neurons is changing. So this second one, the performance of comparison among the various ANNs that have 2 hidden layer. Okay, there are also 2 hidden layer, and also in terms of error and the time taken. But this time, you must write this comparison table. And in addition, for this table, please do use normalization. Okay, so for this one, you need to use normalization, and you can sense that and how important it is to do the normalization. So when you compare table 1 and table 2, this is table 1 and this table 2, and you will have first-hand information about how normalization matters. In addition, I need at least 2 performance curves from this group of ANNs also. So please note the first hidden layer contains varying number of neurons from 10 to 30, the same as this one, and by increment of 5. And the second hidden layer contains a constant 10 hidden neurons. So the second problem, task. The third task is the performance comparison among various ANNs that have 1 hidden layers, and in terms of error and time taken. And for this one, we are going to implement these into our industrial robots. So for this one, I want you the table 3, and you need to use normalization. Okay, because from the task 1 and task 2, and we will get the difference, we will know that and how important the normalization is for this one, and we just use the normalization. In addition, I need at least 2 performance curves from this group of ANNs, and so I'm going to show you on how to get the performance curve. Also, please note that the hidden layer contains varying number of neurons of 15, 20, 30, 40, and 50, and different neurons. Based on table 1, table 2, table 3, and we can select the best one in terms of accuracy and train time, and your choice might be different from mine. Okay, it's totally fine. And for this selected ANN, you need to draw the comparison curve between the predicted value obtained from ANN and the analytical value obtained from the equation. I'm going to show which equation we are going to use. And please make sure the testing data and should be different from the training data. Okay, so training data is the set of data you are going to train your ANN. The testing data is used to test the accuracy of your ANN after you finish training. The weight value, okay, the bias value, and for all connections and all neurons, and for the selected one hidden layer ANN must be explicitly and clearly listed in your IR program, and to be presented in your lab report. So this kind of interesting. So we are going to use this one in our IR environment and in the program. But you don't need to give a lab report. Okay, so no lab report, but you need to have these figures and for your presentation and for your final paper. Last one is the 4 positions you select and for your IR program, along with 4 input values and their corresponding offset values. So the reason I want you to use ANN in this is industrial robot is that because the industrial robot they have the joints. They have multiple joints. Because of these joints, the rigidity of industrial robot is not very good as that of the CNC machine. So as a result, when you use IR to do something, and for example, to do some 3D printing and to do assembly automation, or to do some, this is automatic welding. So you need to take care of this is insufficient rigidity of your IR. How to do that? And we need to do something and to give you some offset. Okay, so the offset. And because when the hand of the IR touches the workpiece, okay, when touches the workpiece, because the insufficient rigidity of the IR, when the industrial robot's hand touches the workpiece, the hand will be pushed back, right? Pushed back. Because it's pushed back, and it means that when this is you use the hand moves, and the new trajectory, the actual trajectory, the actual path of your hand will not be the desired path of the hand because the pushing back from the workpiece. So in this case, how can we offset? How can we compensate this? This is the pushing back of this is industrial robot's hand from the workpiece, and we can give the hand a little bit offset and make it a little bit offset. And this offset, the value of this offset depends on how this is the hand interacts with the workpiece, right? So if the interaction between the hand and the workpiece is bigger, that means the hand retracts retracts a larger amount of displacement. If this case, and you need to give a bigger offset. So this is how what we are going to handle. This is an accuracy because of the insufficient rigidity of the industrial robots. So here, well, I'm going to show you this one. Okay, so so here is what I want you to do, and before I show you how to use MATLAB and to handle this artificial neural network, I give you these two diagrams. The first diagram, and for our case, we have one input and we have one output. So here, this layer, this ANN, and has one hidden layer. Okay, this is one hidden layer. So for this one, and we have this ANN, we have two hidden layers. So this is a layer number one, and this is a layer number two. And so this is one input, and so here is the output. And for our case, because we do not have sensors now, so how can we get this input? So for, in our case, we are going to use nonlinear cubic function polynomial equation, and to mimic how to mimic and how to handle the input and output. Right. So here, so this one, look at this MATLAB code. Okay, this MATLAB code, and this is a capital X is a variable, is an input value. It is from 0 to 100. The interval is 0.01. Okay, so and we will have for this one, this X, and we'll have a huge number of this is the values, and this is X. X is a vector, and it contains the values from 0 to 100, and by the increment of 0.01. So this is X. The T is the target, and T actually is a formula of the equation. So this one equals X dot, this is a cubic 3, okay? So if you have never used MATLAB, and I need to tell you, and these two signs and represent the power 3. Okay, so this is X power 3 plus 3 multiply, this star means multiply, and I have 3.0, and 3.0 means this is a decimal number instead of a whole number. 3.0 multiplied by X, and then we have the power 2, X power 2, and plus 24 multiplied by X, and plus 30. So this is the input value, and this is the output. This is output value. Okay, so this output value, whenever you want to establish this is an artificial neural network and want to train the artificial neural network, and you must have this is the training data. And for this case, this X and the corresponding T will be used as training data. The training data, you must have input value and the corresponding the output value. Okay, so so this is our training data, and then here this net net equals feed net. Feed net is a function of MATLAB, and the first argument is a square bracket 30, 10, and then comma this is apostrophe the train LM. So this is algorithm how to train this this is artificial neural network. So 30 and 10, it stands for 30 stands for the number of first hidden layer. Okay, so for this case we have two hidden layer. For the first hidden layer we have 30 neurons, and for the second hidden layer we have 10 the neurons. I just give you one example, and for our task I ask you and to keep the 10 the fixed and change vary this 30 and from 10 to 30 by the increment of 5, right? So you can vary this one and to get different artificial neural network. So you can use this one and to get artificial neural network, and that has two hidden layers. The first hidden layer and has 30 neurons. The second hidden layer has 10 neurons. and then you just specify these parameters, net, the train parameter dot, and abacus, and this is 80,000. So abacus means that iteration. I want how many iterations I want my the training of my ANN to go. So this is 80,000. This is very, very huge number. And second value is that a net train dot go. This is 1e negative 25. So this is accuracy. I want to see this is accuracy. Okay, how accurate I want my my ANN is. So this is accuracy. So this one is train parameter LE25. You can just use this number. So this is a maximum fill is a 10. You can just use these two numbers, okay? And then after you get specify all these parameters, and then you can use this increment this statement, and using this is a train net IXT. So this is the original net you established, which has 30 neurons for the first hidden layer and 10 neurons for the second hidden layer. So you can use this one. I'm going to show you. Okay, so and you can just copy and paste. But what I give you is MATLAB code, PDF, and you can. I want you to key in all these statements. Now I want to show you guys. Okay, so show you here. Actually, before this is recording, I just tried it. Okay, I can just copy. Now you can see this dialog appears, right? So this dialog appears, and you can see the progress epoch, and from 0 to 80,000. 80,000 is a value we just specify, right? Time. So this is the corresponding time, and the performance. This performance is what we spent 10 1e negative 25. And so this is a plot we are going to show you. It takes some time. Okay, so I'm going to it takes time to run. You can see it is running now, and after we finish, I'm going to show you how to get the performance curve, and we can just stay here and for several minutes. You can see the iterations is increasing. You can see this is increasing now. It will finish very quickly. Okay, also you please make sure and you have access to MATLAB. If you cannot get this free version of MATLAB on your computer, and you can use the computers in the computer lab at Parks College. So I think you have access to the computer lab because you already have this through ID, right? It takes some time, and you can see this one. This first example is that is training the code that does not, use the normalization, and for the code that uses the normalization, it is much faster and it runs much faster. You can see here, training neural network here. Oh. You can see also here, neural network. Input, output, hidden layers. So here is the time, the time it takes. This is a iteration is run. So you can see is this value is decreasing. Oh, it takes too long. Oh, come on, come on, come on. See, you can see this performance, this number is reducing now. Come on, come on. Okay, you can see training level burger marquetted. This is a training algorithm performance mean square error and calculation using MEX. It takes some time, guys. I'm sorry. I should use the normalization as example. So you can stop training for some reason. But let's finish. You can see. So for this one, finish this one. For other examples, and you can try. I will show you another one that uses normalization. You can see the huge difference in terms of time it needs. Oh, 20 minutes. Long time. Long time. Whoa, whoa, whoa. It runs so slow. It's okay. Be patient. I'm to give you one complete demonstration, and then for other, we can go very, very quickly. Come on, come on. So slow. Okay, you can see here is the going down. The performance here is not where the mouse. Here. This one going down. Okay, 30 minutes. Okay. Okay, it takes time. It takes time. I'm going to show you. All right, so it is still running. I can show you the performance here. I click this one, you can see is the performance. No, it actually is not finished yet. So, but I want to. This is a training state. This is a training state, right? The gradient, mu, and validation checks. You can see a lot of things. So this arrow histogram. The arrow histogram. And regression. So this is the fit. The plots, right? This is the plots, fit. This arrow is here. So this one is actually the curve, the formula we are approximating. So it takes some time. Okay, so I'm going to stop training for this one. Let's close it. Now I want to look at the another one with validation. So this one is we have validations here. So oh no, sorry, normalization. So this is x and t, and they are the same as these two statements. So however, additionally, we have these two statements. This one, this one. So this one, you can see map, mean, max. So this one is want to automatically, so the system will automatically and map the x and to an interval between -1 and to 1. So as I said, -1 will be corresponding to minimum value, +1 will be corresponding to the maximum value. All these other values will be mapped into this interval from -1 to 1. Also, same thing for this is the target for the output. And we also use this one as this is the to normalize this t, okay? So normalize this t. So you can see xn and xx, this is the output. And when you use this x, this is input x, and you will, after you call this function, you will get xn and x. For this one, and you will get tn, ts. For xn is normalized x value. So tn is a normalized t value, okay? So he use net, and we also use 30 neurons for the first layer, and second 10 neurons for the second hidden layer, and everything else is the same. But for this is a net, when we treat a net, and we will not use x and t, and we will use xn and tn and instead, because xn is a normalized value for x, tn is normalized value for t. For this one, if we use this one, okay, a copy and this one into the MATLAB environment here, and you will see how quickly it goes. You can see it goes very, very fast. You can see? See? Just 9 seconds, 10 seconds, it can, the accuracy can go here. Will go very, very fast. You can see it go very, very fast. Only 1 minute, about 2 minutes. Let's finish this one. it will go very, very quickly. So this is also two hidden layers, right? So you can see performance. You can also see training state, error histogram, regression, then the feed. The feed, you can see this is our original. This is an equation, but from -1, you can see from -1 to 1. And so this is arrow. So these are two hidden layers. It's a little bit slower, and I'm going to show you for one hidden layer that we are going to use for our IR program, and to see how it works. It's only 6 minutes now. And look at the performance again. See? Yeah, let's stop training on this one. Okay, so then we come back to the Word file. And so now for this one, so one hidden layer and with normalization. So we can use this one hidden layer and with normalization 30. There's only one certain layer, and so this hidden layer has 30 neurons, and we just copy and paste. So here, okay, so this one, I'm going to show you. Paste. See, it goes very far. Do you see how fast it is? Oh, 3 seconds, done. So this is done. So 1.0 next to 12, after negative 12, minimum gradient reached. See, and that'll be good enough, right? So this will be good enough. So go back to the Word file here. So this one below is a complete MATLAB file for constructing and training one hidden layer in with normalization and getting weight values for all connections and threshold value. But it will say for the threshold connection, I'm going to show you this here. So this one, we are going to focus on this one. This connection, and this input has one connection, and to each of these neurons in this hidden layer, and the output also has one connection to each of these neurons in the hidden layer. All right, so that means this is a connection, and in order to calculate, after we train the astronaut, after we train the artificial neural network, we want to get the weight of this connection, and also this is threshold value of this neuron. So threshold value in in the MATLAB is called bias, right? So bias value B. So this is a bias value. So threshold value is called bias value, connection weight. So for the connection weight, right? So weight value for all connections. So you just copy and paste this one. I'm going to redo it. So I'm going to do it again. Copy and paste. See, 303 iterations, 5 seconds. I finish. This is I finished the training. Now, I want to get weight value. So this is using these two statements. And weight 1, net low net LW is the weight for the weight 1. Weight 2. Where we have weight 1 and weight 2. Weight 1, right? So here, so we have this weight 1 means the weight is a vector, okay? The vector from this input and to these neurons in the hidden layer. Output 2 is the weights of this is connections from these neurons in the hidden layer and to the output. So they have 2 vectors, and W1, weight 1, W2, weight 2. And B1 is also, okay, B1 here, okay? On B1, we have neurons here. So this neuron, no, so single layer. Each of these neurons has one bias value, what we call a threshold value. So this output here, we also have a threshold value or bias value, but for input, and we don't have bias value here. You be very, very careful. So we have for B, we have B1 and B2. So if so now, and we can have and this copy, right? Copy and paste. And then go to the here. Now, so all these W1, W2, B1, and B2, and will be saved and to this neuron net data. This is a TXT file. I'm going to show you the file we just got, right? And then you can validate your data. Then you can validate the data. You can verify to test the performance. Okay, so this one W1 and W2, B1, B2, and you will need these values in the IR because MATLAB, and you need to output these. This is the numbers, and then put these numbers into the IR program code, and then you can run your program. And I will show you this text file later after I finish validating this data. Okay, I copy this one to validate. You can see for this X1, and it's different from X. As I said, and the validating data must be at least partially different from the training data. Okay, if you use the training data to validate, it's not good. The reason is that you train the ANN using this data, and then you validate, and then definitely you give you a very, very good results, right? So let me copy and paste here. And so you can see the calculated value and the prediction with ANN, and they are very, very close. That means they are very close. Okay. So here, what I did, I do X1 and T1 and X1 here. Okay, X1 go here, get this is normal, t normal, and then t normal 2, and t normal 2 is using this one. So from this net, from this input, get this output. And then so you have this plot x